Ladies and gentlemen, nice to see you all this afternoon. And we're here to introduce to you an idea. It's a concept. And I hope it will be a bit entertaining as well. But while this is the Council on Tall Buildings and Urban Habitats, I thought it would be interesting maybe for you to just give a very short, brief history on tall buildings and urban development in Stockholm. Just a very quick one before we dig into the idea. To put everything in concept, I will just show you where we are in the world. This is the world map. You see the cross. This is the country of Sweden up in the north. And here we have the city of Stockholm, based on islands, and the cross is where Tyrens has its office. When we look at this old picture, it easily reminds us about the erection of the Empire State Building in New York in 1931. But it is actually a photo from the very first tall building that was done in Stockholm, the Wenner-Gren Center, built in between 1959 and 1962. And when that was finished, this was actually the tallest steel building in Europe at that time. But during the 50s and the 60s, there was a strong optimism about the future in Sweden. The war had ended and we were looking forward. And during this era, those 5 dominating buildings were done in Stockholm. And for you that have been in Stockholm, you have probably seen them. And next to these buildings, you see Sven. Sven is the founder of Tyrens, smoking his cigar, watching and reviewing the drawings. And this was in 1942, when Tyrens was founded. This is a 70-year-old company this year. And today we are a multidisciplinary engineering company selling services within different sectors of competences. And we are about 1,200 employees all around Sweden. We are Sweden-based. But we also own the majority of Adams Carrot Taylor in London. Some of you might have heard of them, high-profile engineers. But at the 50s and the 60s, a long building boom started in Stockholm, which lasted through the 50s and 60s. And it was out with the old and in with the new. And at that time, over 800 medieval buildings were destroyed in Stockholm. And this was actually a common sight in Stockholm at that time. And no other city in Europe lost so many old buildings, unless they were bombed in the Second World War. So it was a city that was used to be for people, with a lot of apartments, flats, etc., that transformed into something else. It turned into big concrete complex, it turned into aluminum facades, etc. The modern look for that time. But this is also probably the reason why politicians and people like today, they are very cautious when giving building permits and when they plan the city center of Stockholm. And especially when it comes to taller buildings. But luckily, we have the summary of what I said. But luckily, we still have some old buildings left. I will just show you some. This is the old market in the old city of Stockholm, with about 3,000 inhabitants, buildings from the 16th and 17th century. Actually, one of the best preserved old towns in Europe. This one, the Royal Palace from 1697, contains over 600 rooms divided into 7 floors. With 9.5 million inhabitants, Sweden is not a densely populated country. Just like the rest of Scandinavia, we don't have many big cities, and therefore, of course, we're not famous for our big, tall buildings. But we have a reputation of being environmental, and we take care of the nature, and therefore, we use our forests that we have in our country in residential and construction. So today we can build up to 8 floors in timber for residential purposes. Today, actually, Stockholm is one of the fastest growing cities in Europe. The lack of apartments is tremendous. We'll have a shortage of 73,000 apartments in Stockholm. And therefore, new ideas of high-rise and higher, taller building is coming also in Stockholm. And it doesn't cost as much residence as it did only a couple of decades ago. And I will just show you some projects that have been just constructed or is being planned. We can't compare them to the highest projects in Asia or the Arabic world, but still, I'll just give you a picture. Residential building, the tallest one in Sweden, but that was completed 2 years ago. This is a new project that is being constructed at this time. They have just left the foundation work. Another project being planned, one of the higher buildings which is being planned in Stockholm at the moment. The famous architects Hertog Meron, also famous for the bird nest in Beijing, are the architect for this one. This is the Tors Tower. That should be the gateway from the neighboring city into Stockholm. And this is a finished project. The Victoria Tower, which is the highest hotel in Scandinavia. And this one is done by the Swedish architect Gert Wingård, also one of few Swedish architects that has some kind of international reputation. And the idea of a high-rise building in Stockholm has created a lot of nice ideas from architects in Stockholm, but today we are not allowed to build higher buildings in the city center of Stockholm. So they want to have them in the outskirts of Stockholm or the neighboring parts of Stockholm. And that's because of the skyline. They want to prevent it from change. And who knows, this might be the future of Stockholm, but still we have some politicians that are against higher buildings within the city center of Stockholm. That was a short introduction of the urban development in Stockholm when it comes to taller building, just to give you a picture. And now I will hand over to Fritz King, the business developer and the inventor of this difficult name, the Articulated Funiculator and the Tubed Megaframe. Please, Fritz.
Thank you, Dag. My name is Fritz King, and I'm a structural engineer with Torrens. And thank you for coming and hearing our presentation on the Articulated Funiculator and the Tubed Megaframe. What is the Articulated Funiculator? The Articulated Funiculator is the new form of vertical transportation for tall, thin skyscrapers. It could be looked at as a train system that moves people in mass up and down the building. You can look at it this way. Look at it as a subway for tall, thin skyscrapers. For example, in a horizontal city such as New York, you may have such things as buses and subways. But in a tall, thin skyscraper, perhaps we need more than just conventional elevators. And what we need is the articulated funiculator and elevators. The question is, where did the idea come from? How was it inspired? The idea was inspired in Hong Kong. Sirpa Salavar and myself, we attended the Conference of Tall Buildings and Urban Habitat Conference in Seoul last year, and we decided to go to Hong Kong on vacation. And it was our first time there, and of course, like many tourists and people who love tall buildings, we were very enthused about all the tall buildings and the amount of densification of the city. It was very easy to get around on walkways, and things worked very well. And also, as tourists, we took the funicular to Victoria Peak. Now, the interesting thing about the funicular, any funicular, is there's a train going up at the same time the train is coming down. And the beauty of this system is the weight of one train is counterbalancing the weight of the other. So the energy requirements for funicular without losses is just for the passengers that are inside the system. The question is, what happens if you take a funicular and turn it vertical and stick it inside a tall, thin skyscraper such as the International Finance Center or the Bank of China or the International Commerce Center? What happens is that's how the articulated funiculator was born. The question next is, what happens when the articulated funiculator is enthusiastically explained to colleagues and co-workers, such as Sirpa Salavara, who's also a co-inventor and co-author, Mats Lundström, the co-inventor and co-author, and Peter Severin, who is also a co-inventor and co-author, and Zainab Tazali. In the words of the noted philosopher and Kyoto Prize winner Sir Karl Popper, what really makes science grow are new ideas, even false ideas. So So let's take a quick look at vertical transportation from the beginning. In the beginning, we have the Otis mechanical lift in 1854, and we have the Otis Brothers and Company elevator that came out in 1900. What's the challenge with super tall buildings when it comes to such things as conventional elevators? As buildings get taller, the number of elevators increases, and what happens when the number of elevators increase, the result is we get lower and lower floor utilization ratios that we can sell or rent to clients. In addition, we start consuming more electricity, and the relative speeds of moving people up and down a tall, thin skyscraper is relatively slow. All of this costs money and makes tall, skyscrapers unaffordable. The articulated funiculator basic concepts. What the articulated funiculator is, it's actually like a subway system which will run up and down inside the building. Here you can see this is a prototype of what the train cars would look like. These are the tracks, and these are docked at stations. Once the trains move out of the station in a horizontal alignment, they curve and then they drop down, as you see in here, to the next station. At the same time, the other one goes up, as this one goes up, and that one goes down. So it's like a figure 8 circling up and down the building. The beauty of this is the weight of the cars going up matches the weight of the cars going down, just like in a funicular. So therefore, the only energy requirement that would be necessary is only for the passengers once again. So now, the thing is this. When you're inside the train, you'll be standing just like you would in a regular elevator. But as the train turns to the vertical alignment, in order to remain standing, we have to have some pitch in the cars and in the system. So this is an example of and also in addition to that, at the top and bottom stations, there has to be a transition because the shaft alignments will not match. So the question is, how do we handle these things? This was a prototype of the car design. And if you think about it, a box in a sphere can move in 3 different directions. It has both pitch, roll, and yaw. So therefore, the pitch is what we need in order to keep the cars vertical so people remain standing. But to negotiate the transitions at the top and bottom of the building, we may need yaw and we may need roll if that transition is done in the curves. But we decided if the transition is done in the vertical alignments, all you need is roll. So therefore, the prototype train would be cars such as this, that all of them have a pitch to roll so that you remain standing, and pitch so you remain standing, and then there's a roll between the actual train cars in order to negotiate the transitions at the top and bottom of the building. These were some hand sketches as we were moving along with this, and this is a rhino model of sort of what a conceptual design, the train may look like. The question is it possible to design a high-moving rail-type system with pitch? And the answer is definitely yes. Myself and colleagues, we went to Gröna Lund, which is an amusement park in Stockholm, Sweden. And now there you can see it. There is a system such as that. Coincidentally, it's just named Insane. Here's another photo of the Insane ride at Gröna Lund. Acceleration and velocity strategies. Since the weight of the articulated funiculator trains are balanced, what happens when one person steps on one car? The whole system starts to accelerate at 1g, assuming there's no losses in the system. So the fastest speed of this is going to be 1g. So this rise means these cars are going up, as you can see in part of the loop, the fall, or these are going down. So what would happen is when you step on the car, the downbound cars will be dropped, and they would go down at 1g, which would produce a 0g environment inside of the car. And then halfway down, they're decelerated at 1g, producing a 2g environment inside the car. The beauty is if the stations are pitched or separated by 200 meters, it would take 9 seconds to achieve this, and a maximum velocity of 159 kilometers per hour could be achieved. If it was 500 meters between stations, it would take 14.3 seconds, and the trains could reach a speed of around 250 kilometers an hour. Question, is it possible to design a mechanical system that can actually sustain that kind of 1g acceleration? And the answer is yes. Going back to Gröna Lund, this is the free fall ride that myself and colleagues went and rode on. Here we are there. And what you can see from these photos is that the feeling of falling at Going down at 1G in a 0G environment ranges from exhilaration to fear and fright. So the point is perhaps the 1G is not the answer, but there's some percentage of the 1G that will work. Essentially what we're proposing here is a bullet train to the sky. In the words of Nobel laureate Eugene O'Neill, happiness hates the timid, and so does science. Okay, acceleration and velocity strategies. From the table we saw before, if we estimate about 15, see the train comes to the station. Then the doors open, people unload, people load. Then the system has to slowly transition to the vertical alignment, which takes time too, about 10 seconds for 2 alignments. Then the system is dropped, okay? And that takes about, depending upon the distance between stations, 200 meters to 500, that takes between 9 and 14 seconds. So the total cycle between the train can range between, say, 29 to 40 seconds, so 39 seconds. So what happens is you go to the elevator banks, and it looks exactly the same as they do today in buildings. All the doors open at once, the people come out, people go in, it leaves. Then there's a sign that counts down like 29, 28, until the next train comes. And the next train, the downbound train is on one side, and the upbound train is on the other. Interesting though, this particular concept says we have to get rid of the central core. And the central core is one of the main problems in tall, thin skyscrapers, because as buildings get taller and taller, the building has to sustain more and more elevators. So eventually, the building basically becomes a house for conventional elevators. So what we have here is a new type of structural system that is also compatible with or without the articulated funiculator, and we call this the tube megaframe. This prototype building that we were studying is 620 meters high. It has a floor plan of 45 meters by 40 meters, and it only has 4 vertical tube legs, and then it has what the stations, which we'll look at, and it has some cross tubes for stabilization, the same way you would put intermediate outriggers on current systems. Because the system is so efficient, we're offering slenderness ratios of 1 to 15.5 and 1 to 13.8. The prototype building looks like this. You can see the main tubes here, high strength gravity, and then the beauty of this is all the gravity loads are being transferred to the perimeter of the building, to the main legs at every station and cross section. What does that do? That gives the efficiency of increasing the building stance, which increases the efficiency and makes the whole system extremely effective. This is our initial structural performance of it, running structural analysis on this type of building. Each of the 4 vertical legs were about 10 meters by 6 meters, and they range in thickness from 1.5 meters at the base to about 300 millimeters at the top. As you can see, under a wind speed of 37.1 meters per second, we're expecting a concrete strength requirement of C60 to C70. And at the wind speed of 34.6 meters per second, we're getting maximum drifts of the building of H over 400 in the 40 meter direction, H over 580 in the 45 meter direction. Power braking systems. This system is sustainable, and the reason is because, as you can see, this is sort of a diagram of how the system would snake up and down the building. There'd be 1 train here, 2, 2, 1. The thing is, when you drop the payload, and it goes down half the fall, we don't brake it using standard brakes, we use dynamic braking. We use the potential energy that was already in the system, and that then pulls a generator. It's just like pouring hydroelectric energy, but when we're using the people as the water. So it generates a generator. That energy is stored. So after lunch, say for example, people are going down before lunch. So they go down, they're dynamically braked, that energy is stored. So after lunch, when people come back, that same energy is required to take them back up, because the universe is already balanced in energy, so we just have to figure out how to use it. As you can see here, there's a station with 2 trains together, 1 train going down, 1 going up. This is a conceptual design of what the power braking system may be like. This shows you the system inside the station, trains going up and down. And here's kind of a diagram of a station. It's a 3-story concrete box connected to the vertical boxes. You can see the doors here. You come out here, and you can then go from here, you can come out, and you can then transfer to the other side of the building through these doors here or there. And in addition, you transfer to the other legs where we house the conventional elevators. This has stations, so therefore we're using a combination of this new system and conventional elevators. You can see here's a diagram of what the station may look like. Escalators, so you come out in the middle, you take an escalator up, conventional elevators up, take an escalator down, conventional elevators down. In addition, all the mechanics for the power braking systems will be housed inside the tubes, so they will not be out in the interior, reducing usable space. Here's another rendition of the station. Floor utilization ratios. With this system, we've gotten rid of the central core, moved all the loads to the outside. If you see here, if it's a 50 by 50 floor plan, then we get a floor utilization ratio of about 0.877. Most high buildings, we did a sort of a summary. We have numbers that are range from 0.5, 0.6 to 0.75. Therefore, by this structural system will produce about 30% more rentable, sellable floor space than current systems being used today. Here's a transportation plan showing how the system would work. Station here, station here, station here. In between the stations, conventional elevators. 620-meter building floor plan, 40 by 45 meters. 22 conventional elevators. 6 articulated funiculator trains. And the thing is that there's more than one way to move up the building under this type of system. You can either take if you're up here, let's say, you could take the train system to here, then conventional to here, or you can take the train here and come down, or you can just take the conventional elevators all the way up with transfers. Because there's more options, this will produce more passenger volume, which will reduce congestion. The other thing is this system, the tubed megaframe, can be adaptable to almost any kind of architectural form. We're showing a box, extruded box, but that is not the way it has to go. It can use any kind of basic forms that an architect can come up with. And another thing that I think is a very important enhancement here is that when you get rid of the central core, then you have open floor plates, and now we can move new programs into the so-called vertical building, such as concert halls, hospitals, large swimming pools, open theaters, because we don't have the central core. Therefore, now the building becomes a true vertical city. Conclusion. The articulated funiculator, we have reduced number of conventional elevators, reduced number of elevator shafts, increased rentable, sellable floor space areas, dynamic braking, so we reuse the energy, ultra-fast speeds, short cycle times. The tubed megaframe, only 4 vertical tubed mega columns. No outriggers or outrigger connections, no belt trusses, no central core, smaller floor plates. Because it's so much simpler, it's going to be easier to build and faster to build. And all loads go to the perimeter of the building, making it sleek and very effective. In the words of Albert Einstein, we cannot solve our problems with the same thinking we used when we created them. The sky's the limit. Thank you for your attention.